Hello everyone. In this video, I'm going to continue talk about sorting algorithms, and I will cover heap sort, the last sorting algorithms that works in n log n. So remember we have talked about the sorting algorithms. We discussed about the in-place sorting algorithms, which basically is going to be the sorting algorithms that they don't need additional space in terms of the number of items that they are sorting. We have seen merge sort, which is an n log n sorting algorithm, the best time complexity that we can get, but unfortunately merge sort is not in place. Then we discussed about the quick sort, which if you find a good value close to the median, you can run the you can make sure that the time complexity of quick sort can be n log n again. The quick sort, the good thing about the quick sort is that it doesn't have the merge part from the merge sort. Basically, it's just a modification of the merge sort that we get rid of the merge part, so it can be done without additional space. But still, the quick sort needs some space because of the recursive calls, because of the recursive functions that you have. So still quicksort is not exactly in place. If I wanted to actually introduce you a pure in-place sorting algorithms, none of the merge sort and quicksort can be done in place. Although we usually actually say that the quicksort is almost in place because the space complexity can be theta of log of n, which is kind of negligible considering the fact that log of n is very small, but still that's not exactly in place. So today I'm going to show you, in this video I'm going to show you another sorting algorithms that works in n log n, and this is pure in place. This is called heap sort. Remember we have talked about the data structure binary heap, which is going to be a binary tree with some specific properties that if it is a min heap, for example, every item, the item at the root node is going to be the smallest item, and everything on the root node is going to be larger than the root, and this property is the case for every node in the tree. If it is a max heap, just the reverse of that. The item at the root node is going to be the largest item, and for each of the nodes in the tree, the item is going to be the largest item among all the items in that corresponding subtree. So the whole idea of the heap sort is that we are going to use the data structure heap, binary heap, to be able to sort the items in or the items which we are going to sort. So basically we create a binary heap, we put all items into the binary heap, and then for example a min heap or a max heap, and always just take the minimum item out, right? And it can kind of give us the correct order of the items. So the whole strategy is to create a binary heap, put all the items inside that, and then remove those items, all the items one by one. And in this way, we sort them. But there are some details here that we need to take care to make sure that the time complexity is exactly n log n, and make sure that the algorithm can be sorted, can sort in place. So first about the time complexity. You know that the time complexity of removing an item from the binary heap is going to be log of n if you are going to have n items in your binary heap, right? So think about this idea. Just assume that we have created a binary heap. We know that the time complexity of creating a binary heap is theta of n. the build heap. Remember, we have discussed the time complexity of build heap. So I'm going to skip that part. So putting the items, creating a binary heap from an array can be done in linear time. So that's not my issue. The problem here is that you have n items, you have created your binary heap. Now you are going to remove the items one by one, and I'm going to see that what is the time complexity in that case. At the very first, your binary heap is going to have n items, so that the time complexity of calling pop and removing the first item is going to be log of n, right? Then you are going to have n minus 1 item, and you call the pop again. So that is going to be log of n minus 1, because you have removed one item from the binary heap. And then you removed one more item, so the number of items is going to be n minus 2. So another pop, the cost is going to be log of n minus 2. So again, until you just actually do the same, until you reach to log of, for example, 2, then log of 1. So this is the summation that I have to write. So basically this is going to be that summation. Instead of log in base 2, I have written it as log in base natural number. So I have written it as ln. It doesn't really matter. You know that the different logarithms can be converted to each other easily. It doesn't change the time complexity. So this summation, you know that the summation of log of a plus log of log of b can be written as log of a multiplied by b. So basically all these items that inside the parentheses of the log, instead of putting the summation outside, I can take the summation and make it a product and put it inside the parentheses. Basically, instead of the summation of log of n plus log of n minus 1 plus log of n minus 2 until log of 1, I can write it as log of n multiplied by n minus 1 multiplied by n minus 2, the multiplication of all these numbers, until 1, right? So basically, this part inside the parenthesis is the definition of n factorial. So in total, I got to log of n factorial. Now I wanted to know that what is the time complexity of log of n factorial. It is possible to prove it using some mathematical things, actually drawing the diagram using some software like Maple, but a very simple trick here is I cannot find the theta of log of n factorial exactly, but I can find O of log of n. So what I know about n factorial is that n factorial is smaller than n power n, right? You can simply just say that, okay, n factorial is the multiplication of n to n minus 1 multiply, so you really should excuse my handwriting. I don't have enough space here, so that's why it makes it even harder to write. So n factorial will be n multiplied by n minus 1 multiplied by n minus 2 and so on. Okay, so if you think about it, this is definitely going to be smaller than n multiplied by n multiplied by n multiplied by until n, right? Because all of these terms are going to be smaller than n, except this one. So basically, for sure, n factorial is going to be smaller than n power n. So I can take the log of n from both sides. So the log of n factorial is going to be smaller than the log of n power n. And again, we know that log of n power n can be written as n log n, right? Because basically, whatever is the logarithm, you can write log of, for example, n power k can be written as k multiplied by log of n. Whatever is the exponent, the power here for n, you can actually take it out of the log and write it as the multiplication of the log. Okay, so log of n factorial is definitely less than n log n. I can say that log of n factorial is in O of n log n. That's enough for me. Basically, it is the time complexity of the heap sort. I showed you that if you keep removing the items from the heap sort, the time complexity is going to be O of n log n. Actually, the time complexity is going to be even not theta of log n log n, O of n log n. Okay, now let's actually just get back to this question that can we do the heap sort in place? Remember, we say that a sorting algorithm is going to be in place if we are not using additional memory in terms of the number of items. We know that if I have an array of items, the method build heap can convert the array into a min heap in place without using additional space. Okay, so that's good. That's it means that creating the binary heap can be done in place. But what about removing the items? If I remove the items from the binary heap, where I'm going to store them? This is where the question, actually this part of the question comes to mind, that for writing the heap sort in place, instead of using a min heap, I am going to create a max heap. What is a max heap? Remember, the min heap was something like this, that, for example, 2, I don't know, 3, 15, 17, 20, 10, 6, something like this. So even without these notes, this is a min heap, right? Always every node is going to be smaller than all the nodes in the corresponding subtree. So 2 is the smallest one in the full tree, and then 15 is the smallest one here, and then, for example, 3 is the smallest one here. This is a min heap. Instead of having a min heap, I am going to create a max heap. The time complexity of creating a max heap using build heap is exactly the same as creating a min heap. There's no difference, right? But there is a good thing about a max heap instead of a min heap. If you had a min heap, when you are removing the item, let me actually show you the example. You assume that you have this original array, and then you call the build heap over it, and you create a max heap from your array. Okay, you create a max heap from your array, something like this one. If you remove the item from the max heap, what would happen? Remember, in the method pop, you take the value from the root, and then you remove the last leaf node. This is a binary heap stored as a complete binary tree, right? So the last node is going to be 3. So basically the node 3 will be copied here, and then it will be percolated down until it will actually just placed in its correct position. And then what would happen? The thing is, the position of this last leaf node will be empty, right? So it's just like inside the original array that you have, you emptied one space, and that space is basically the last index, which is exactly the position for the largest item that you have just removed. Just take it and put it at that last position. That's it. That's actually that trick, that instead of using a min heap, if you use a max heap, the item that you remove from the tree can be just immediately copied and put at the position that will be released from your binary heap. So this is exactly the position of that last leaf node that has been released, right? You have actually copied 3 up, and then 3 has been percolated down, and then 95 will be just copied inside this empty place that you just released. And this is exactly the position for 95. This is the position for the largest item. Then you just actually, let's call another pop. You again pop an item, so 81 will be popped. The next leaf node, which is going to be this position, again this one will be copied to the root. Then it will be, this part will be actually just emptied, right? The value of 3 will be percolated down. You compare these two items, again 3 will be actually just swap to this one. 70 will be here, and then it will be swapped with 52, so 3 will be placed here, 52 will be placed here, and this position will be released. So instead of 3 here, then 81 will be copied. 81 will be actually just copied here. So this is exactly showing you that the next step, that 81 will be copied. Then the value of 3 will be percolated up. Will be actually copied as the root node. Then it will be percolated down. Then 81 will be just copied as the next position. It actually just shows you all the steps of removing, popping an item from your max heap, and just put it at the position that has been released. Removing an item from your max heap and put it at the position that has been released. You know, here I have actually just completely get rid of this shape of the tree, because basically when you are going to have a binary heap, what you are working on is an array. You don't really have a tree, although the tree has been stored as an array, but basically what we have is this array. That's why I thought that just showing it as an array is going to make it more clear. I mean, give you this idea that we are really working on an array. So it just shows you all the steps. The next item is going to be 52. The maximum item removed from that max heap, and then will be copied in the correct corresponding position. Then 46, then 34, 28, 17, and the last item is going to be 3. So just as an exercise, you may just assume that this is going to be the very first array which is given to you. Then run the build heap, create a max heap inside that array, then just repeatedly remove the maximum item, put it in its correct position. Just try to trace the algorithm over this example, just as an exercise for yourself. To summarize the heap sort, the idea of this heap sort is very simple, because we already know that data structure, a very interesting data structure, binary heap. You can create the heap inside the array in linear time. We have discussed this, and then we can repeatedly pop an item and just put it in its correct position. How many pops we have? We have exactly n pop. The time complexity of the first one is log of n, the second one log of n minus 1, log of n minus 2. We have already discussed that the summation of all these is going to be O of n log n. Therefore, the time complexity of creating the max heap, the time complexity of removing the item and put them in its correct position is n log n. So in total, the time complexity is going to be O of n log n for the heap sort. So if we wanted to discuss about the worst case, average case, and the best case, the thing is there is no worst case scenario. Always the time complexity of removing an item from the heap sort is going to be log n. So in total, the time complexity is n log n, and there is no worst case. The worst case and the average case, both of them are the same. The time complexity is n log n. There is one special case for the best case, and that is when all the items are equal. If all the items are equal, basically the time complexity will be reduced to linear, because the time complexity of the pop will be basically constant, not log n. If all the items in the binary heap are equal, the time complexity of pop will be just one pop will be constant. You are going to pop n items. In total, the time complexity is going to be linear if all the items are equal. So there is this question basically are more like the questions that are asked, the tricky questions that are asked in the interview of coding algorithms, that what is the best case for the heap sort, what is the time complexity of removing or pop from a heap sort if all the items are equal. This kind of questions are more like tricky questions asked especially in the interview questions for some programming positions, developer positions. So this is the summary of the heap sort. There is no worst case. Basically, the worst case and the average case, both of them is n log n. The best case is going to be linear if all the items, and the scenario is that all the items are equal. All the items are the same. The space complexity is clearly just 1, because you don't need to use any additional space. There is one thing about the heap sort compared to quick sort and merge sort. Although the heap sort is pure in place, this is and although the time complexity is n log n, O of n log n, the same as the time complexity of quick sort and merge sort, but basically quick sort and merge sort in practice are faster than the heap sort. So all the in-place sorting algorithms in the built-in sorting algorithms that is used in programming languages are going to be some modification of the merge sort or quick sort. They don't use the heap sort. Heap sort is not really the best sorting algorithms that you can take. Usually you should just go with the quick sort or merge sort. Both of them are kind of related to each other. They are modification of each other, and they are faster than the heap sort. I mean, in practice they are faster, although the time complexity of all of them are the same. There are some additional slides here that you can check that shows you, just as a reminder, how the build heap works. If you wanted to see more examples, you can follow them. But that's it for this lecture.